Hello everyone, welcome to our first lecture of Module 3 of Foundational Mathematics, in which we are going to discuss matrix decomposition. In first few modules, we have emphasized a lot on vectors, vector transformations, how we can project the vectors, and we will use those concepts as the building blocks to understand about matrices. Now the question arises, why we need to learn about matrices in a data science course? And secondly, even if we learn about matrices, what we will learn about them. Third thing is that so what? Even if we learn all these fundamentals about matrices, how they are going to help us in our data science representation or data sciences course. Now, when we talk about machine learning or data sciences, one thing that is ubiquitous is of course the vectors. And the second thing that we cannot get rid of is matrix. All the data set, they are represented in form of the matrices. For example, we will be dealing with multiple samples and each sample in turn will have multiple dimensions. Sometimes these dimensions in the context of data sciences and machine learning, they are also referred as the features. Now these dimensions should not be confused with the dimensionality of vector spaces that we have discussed in the units before. These dimensions, they represent the attributes. For example, if we want to build a house price classifier, these attributes would be number of bedrooms, number of bathrooms, size, and distance from the best school in the locality, and so on. Also, once we realize that this data can be represented in form of matrices, these representations are often complex. And we will be dealing with multiple dimension data with sometimes hundreds of features. And if we arrange these features along the columns, then we will also deal with millions of samples. So for example, in this big data world, getting a lot of samples is not really a problem, especially with the domains which have been studied very deeply by scientists across the globe. So when we arrange this information, millions of samples and hundreds of features into a matrix representation, we are essentially looking at very, very large matrices of size of millions cross hundreds. And this quickly becomes very non-intuitive. If you just look at these matrices, they would not convey anything other than just the collection of numbers. Hence, we need to decompose these matrices into some simpler entities. And what this decomposition would mean, we can always relate it back to the theory of factorization. For example, if we have a number 24 and we want to break into simpler components, we can easily say that this 24 can be written as 6 times 4, which in turn are relatively simpler as compared to the number 24. Now applying the same analogy here, we will always try to decompose these big matrices into some smaller components. Let us say that we say that this is U, this is sigma, this is V transpose. So we have to learn that how we would decompose these transformations, or how we would achieve these kind of decompositions. Another thing that we would want to calculate is that we want to summarize these matrices. That is, this is an M cross N matrices. As we learned in the case of norms, that norms are certain transformations that can help us get one dimensional or one real number representation of complex vectors. Can we extend the same understanding or same analogy here when it comes to matrices? Of course, yes. So what we will try to do, we will try to learn about determinants. We will try to learn about the traces, and then there is something very characteristics to each and every matrix, what we call as eigen values and corresponding eigen vectors. And these are the concepts which are solely described for the square matrices, but we will try to look into that how eigenvalues and eigenvectors help us characterize a matrix using some real numbers. Now, when we talk about eigen, word eigen itself means characteristic. So eigenvalues, if we expand it, would mean the characteristic value of a given matrix, and hence we will use this as an important attribute to understand matrices in simpler terms. Now, going towards our mind map, that how these concepts that we are going to learn in this chapter will help us to achieve our machine learning goals. So we will start our discussion with most familiar concept, if you have ever dealt with the matrices, is the calculation of determinant. But we will look into some of the non-trivial insights about determinants. From determinants, we will use the concept of determinant to determine the characteristic polynomial, which in turn would help us determine the eigenvalues. Once we know the eigenvalues, we will use the definition of eigenvalues to come up with the eigenvectors or determine eigenvectors. These eigenvectors, we will see that they, for certain matrices, they will construct the orthogonal matrix. We have already spoken about the orthogonality in the context of vectors, so we will extend that discussion to our metric space. From eigenvalues, we will also learn a very interesting concept, what we call as diagonalization. And diagonalization, as the name suggests, that we will create a matrix which will have a lot of important information along the diagonals, and everywhere else those numbers are going to be zero, which in turn will lay to the foundation of the word that you have heard maybe million of times so far, is singular value decomposition, which is directly used to come up with dimensionality reduction. And specifically, we will talk about the K-rank approximation of complex images, which can in turn be represented by the matrices also. So this would be our last topic that we will learn in this particular chapter. With that, let us begin into some of the fundamentals that what we are going to learn here. So let's get started with the